All right, hi everyone. Thanks to the organizers for the invitation to speak here. Today I'll be talking about the algorithmic phase transition of random k-sat for low degree polynomials. And this is joint work with my advisor, Guy Bressler. In random k-sat, we sample a k-CNF with m clauses by sampling all the literals, IID, and uniformly from a collection of n propositional variables and their negations. So this problem is parameterized by a clause density, the number of clauses divided by the number of variables. And we can immediately ask two natural questions about this problem. First, at what clause densities does a satisfying assignment exist? And second, at what clause densities can such an assignment be found by an efficient algorithm? We call the limiting clause densities here opt and alg. It turns out opt is much bigger than alg. So a third natural question is, what prevents efficient algorithms from succeeding beyond alg? We'll work in the following double limit. We always take k to be a big constant, the clause density alpha to be a function of k, and having fixed both of those, we send n to infinity with the number of clauses m growing proportionally. In this double limit, the value of opt is known exactly. It's this value here, about 2 to the k log 2, which was established by the landmark paper of Ding's, Lai, and Sun. Our attention will be focused on alg, for which a lot less is known. The current best algorithm is fix by Coja-Oghlan, and it finds a satisfying assignment at clause densities about 2 to the k log k over k. Note that this is almost a whole factor of k smaller than opt. But we have heuristic structural evidence that this is the best we can do. And this is because the solution space undergoes a dramatic phase transition around 2 to the k log k over k. Namely, below this threshold, the solution space looks like a single big cluster, whereas above it, it looks like exponentially many small disconnected clusters. And in the shattered regime, local search heuristics become powerless. And this is some evidence that algorithms should not succeed. We'll confirm this heuristic picture to a large extent. We show that because of shattering, the class of low-degree polynomial algorithms can't solve random k-sat at a constant factor clause density, about 4.9, larger than 2 to the k log k over k. And this is part of a long line of algorithmic lower bounds on random k-sat, of which our contribution is the first against any class of algorithms that gets within a constant factor of the truth. So what are low-degree polynomials? Low-degree polynomials are a computation class where all the outputs are polynomials of degree at most d in the inputs. Here, by low degree, we think of d as being about log n. And this is a powerful computation class. It can simulate many of the state-of-the-art algorithms for k-sat or other average case problems, notably including fix. And we'll show hardness for the following notion of solve. We can encode a k-sat formula as a vector of indicators using a one-hot encoding. So we allocate 2n indicators for the 2n possible values of every literal. And we say that a low-degree polynomial solves a k-sat formula phi if the sign of the polynomial output run on this vector of indicators is almost a satisfying assignment. Here, almost means that we're allowed to be wrong in a small fraction of output bits. And after we correct those bits, the resulting assignment has to satisfy all, all but a small fraction of clauses of phi. Note that this is some relaxation of the notion of solve. And by relaxing this notion of solve, we make any hardness result against this notion of solve stronger. We also require the following normalization condition, which we won't really worry about. But I'll say that fix and the algorithms mentioned above can be simulated in a way that respects this condition. So our main result is as follows. define kappa star to be this constant about 4.9. Then at clause density kappa 2 to the k log k over k for any kappa bigger than this kappa star, no low-degree polynomial can solve random k-sat with this success probability that scales with the degree. Note that this probability is quite large, and a limitation of our methods for low-degree polynomials is that we can only rule out a quite large success probability. We'll also show that the more restricted class of local algorithms, which nonetheless simulates fix, can't solve random k-sat with even very small probability, e to the minus cube root n. Also, I'll say that at clause densities where algorithms succeed, they can be implemented by both of these computation classes and do succeed with probability larger than even that ruled out by the first theorem. I'll give some ideas of the proof. So the proof is based on a connection between shattering and the absence of certain constellations of satisfying assignments. And we proceed in 2 steps. So in the first step, we show that at the claimed clause density, there doesn't exist a constellation of satisfying assignments with a carefully chosen overlap structure. The choice of constellation here is critical because this choice is what will capture the shattering phenomenon. And choosing the wrong forbidden structure here will get you something that is not forbidden at the clause density that we want. And second, we show that if a low-degree polynomial solves random k-sat at this clause density, then we can leverage it to construct the forbidden constellation. And therefore, no such algorithm can exist. So this technique is part of the overlap gap property framework, which has recently been used to show hardness for a lot of other problems. See this survey by Marnik. Next, I want to sketch a simplified version of the proof. This will show that low-degree polynomials fail at this intermediate clause density, which is below opt, but still substantially above alg. So the proof goes as follows. We can construct the following path of correlated k-sat instances. And we'll generate this by generating the first k-sat instance, phi0, from the k-sat distribution, and every subsequent one by resampling the tth literal of its predecessor. So in other words, we resample the literals one by one until after km steps, we've resampled all of them once. That means that the first and last phis are truly independent, and the ones in the middle are some mixture of these two. And the key fact that we'll use is that the following forbidden structure doesn't occur. The forbidden structure consists of 2 assignments, each satisfying some phi, not necessarily the same one, that are a medium Hamming distance apart. Medium means some critical value that we'll determine later. And this structure is forbidden just by a first moment argument. So we can plot the log expected number of pairs of satisfying assignments at every overlap value. And we find that the plot looks like this. So wherever the plot is negative, this expectation will be exponentially small. And that means that the overlap structure of 2 satisfying assignments at that overlap won't occur with high probability. And here's how we'll leverage this structural property to show that algorithms can't succeed. So suppose a low-degree polynomial solves random k-sat with sufficiently high probability, namely the probability in theorem statement at this clause density. Then we can run the algorithm on all the k-sat formulas in our interpolation to get a sequence of assignments. And by a union bound with high probability, all of these assignments will satisfy the corresponding k-sat instance. And in this cartoon, I've drawn the first k-sat assignment, x0, and I've drawn a red mote of assignments at medium Hamming distance from x0. I've also drawn the last assignment, and this will be far from the first one because the corresponding k-sat formulas are truly independent, and independent k-sat formulas don't have satisfying assignments that are too close. And now if we follow the sequence of x's, will only ever move by small jumps because of the stability of low-degree polynomials. And this is the property of stable algorithms that we'll use. So this means that we can never jump over the moat, but we eventually get to the other side. So at some point we land in the moat, and when we do, x0 and whichever x landed in the moat, these are a pair of assignments, each satisfying some phi that are a medium distance apart. And that's a contradiction, so the algorithm cannot actually exist. And next I'll explain how to improve this from the intermediate clause density we considered to the clause density we actually care about. So the proof I just outlined breaks down above or below that intermediate clause density. And this is because if we plot the same log first moment now at the clause density we actually care about, it looks like this. So it no longer goes negative. And that means that the structure that we're trying to rule out is no longer forbidden. The key idea to save this is to consider a forbidden structure now with many medium overlaps. The intuition here is that this plot still has a dip, even though it doesn't go negative anymore. And that means that even though medium overlaps aren't forbidden, they're still kind of rare. In fact, because the y-axis is on a log scale, medium overlaps are exponentially rare. So that means that if we can build a structure with a lot of these overlaps, then hopefully we can boost the unlikeliness until we get some log first moment that goes negative. And that's what we'll do. So constructing the appropriate structure where that doesn't occur will require a careful analysis of the energy landscape of random k-sat. And carrying this out is the crux of our proof. And finally, we can adapt the interpolation argument on the previous slide to show that a low-degree polynomial solving random k-sat can also construct this more complicated forbidden structure. I'll wrap up with some open problems. So the first main open problem is to close this 4.911 factor gap. Also, we can think of extending the techniques here to other random CSPs because the picture of shattering implying hardness is believed to hold not only for random k-sat, but for constraint satisfaction problems in general. And also there's a question of when does clustering not imply algorithmic hardness. So as Xiangping will explain in a few talks, this picture seems to not hold for the perceptron, where in some regimes shattering occurs, but algorithms can still find a good solution in some situations. So, okay, that's all I have to say. Thanks for your attention, and I am open to any questions.